Hi everyone, let's continue our next section, 1.4 continuity and one-side limit. Let's look at the first definition. Definition of continuity. Continuity at a point. So a function f is continuous at c. C is a point here if the following three conditions are met. So you have three conditions here. The first one, f of c, is defined. The second one is limit as x approaching c. X approaching c, if I don't have plus or minus, is mean from both directions, f of x exists. The last one is limit as x approaching c, f of x equal to f of c. So basically you do direct substitution c for x. So you have f of c. So for discontinuity, you can be removable or non-removable. Let's look at our example. Find the x value, if any, at which f is not continuous. Not continuous is the same as discontinuous. Which of the discontinuity are removable? So let's look at our first function here. F of x is equal to this rational expression. So I'm gonna factor the denominator. So I have x minus 1. The denominator is trinomial, so I'm gonna factor into binomial. So I have 2 here, I'm gonna put 2 here and 1 here, plus 2 minus 1. That should work. As you can see that we don't want denominator to be 0. If x equal to negative 2, this denominator will be 0, then it will be undefined. So f of c would be undefined. If x equal to 1, the denominator will be 0 as well, so it will be undefined. But as you can see, both of this is discontinuous. However, this one I can reduce. So the one that I can reduce is called removable. And the negative 2 here I can reduce, so it's non-removable. Alright, so two number is discontinuous, negative 2 and 1. One is removable, the other one is non-removable. Now look at the next function. I have f of x is equal to 1 over x squared plus 1. Now in order for denominator to be 0, I need negative 1 here. That nothing, real number square is not going to have negative 1. So this is continuous for all real number. Alright. The next one, I have a function that is rational expression. I'm going to factor the denominator again. So I have x minus 6, x plus 6, x minus 6. Alright, so if x equal to negative 6 or x equal to 6, it's going to be discontinuous because denominator will be 0. So x equal to negative 6, x equal to 6, this is going to be discontinuous. However, I can reduce this. So x equal to 6 is removable. And I can't really cancel this, so this is non-removable. Alright, the last one, I have a function f of x is equal to cosine pi of x over 2. This one, I don't have radical, I don't have to worry. 2, you're not gonna make 2 always equal to 2, it's not gonna be 0. So this is continuous for all x, right? Let's look at more example. Hi, let's continue our next section, not next section, the next definition. One-side limit and continuity on a closed interval. So if I say limit from the right, you're gonna have x approaching some number and have plus. This means from the right of a function equal to L. Now limit from the left, you're gonna have limit x and arrow and then c negative. This means from the left of a function equal to L. So if limit approaching a particular number from the right and from the left and get the same number, you say that limit is exists, which means the function is continuous. If you don't get the same number, then limit does not exist. All right, let's look at our graph here. The first example, as limit of f of x approaching -1 from the right. So you're gonna follow the graph from the right. This is the right, from the right, all right, to -1. Then f of x would be 0. The next one, limit as x approaching -1 from the left. So you're gonna start from the left hand side and follow the graph from the left, and then f of x would be 2 because we start from the left. All right, it would be 2. So as limit of f of x as x approaching -1 from the right and from the left, you end up with two different numbers. So the limit of f of x does not exist because you have two different numbers. And if I don't put plus and minus here, it means from both sides. So because the limit doesn't exist, we say that f is discontinuous at x equal to -1. So it's discontinuous at x equal to -1. As you can see in the graph, it's discontinuous. Now let's look at my second example. I have this graph. If x approaching -2 from the right, so you start from the right hand side, you follow the graph from the right, f of x would be -2. All right, now limit as x approaching -2 from the left. So you start from the left, follow the graph from the left, f of x will also be -2. So limit as x approaching -2 from the left and from the right is equal to -2. We have the same number. So f is continuous at x equal -2. Okay. Next is our theorem. Theorem 1.11 is called property of continuity. F and G are continuous at x equal to c. So if you have two functions and they both continuous at x equal to c, you multiply by scalar, b is my scalar here, is still continuous. If you add the two continuous function or subtract, it's going to be continuous. Same as product, same as quotient. However, the denominator, function of denominator cannot be 0. Theorem 1.12 is talk about continuity of the composite function. If you have two functions, let's say function f and function g, they're both continuous, and if you do composition, either f of g or g of f is gonna still be continuous. The next or the last theorem here for 1.4 is theorem 1.13 is intermediate value theorem. If f is a continuous function on an enclosed interval AB, so I have a function here is continuous on a closed interval A and B. We have a closed interval here. F of A not equal to f of B. So this is my A, so f of A is over here. I have my B, f of B is over here. And they're not the same thing. They're not equal. And k is any number. K is any number between f of A and f of B. So I have k here as and is between f of A and f of B. That is at least one C, all right? C can be anywhere within A and B here. then f of c will equal to k, where k is f of c. So it's any number is continuous from a to b, and f of a and f of b. Alright, we finished 1.4. I'll see you next time.